All right, good morning, hello, good evening, whenever you're watching this, hopefully soon. I hope everybody's doing good. Um, on to our next lesson in the derivative units. All right, so we've become pretty good experts at all the little shortcut rules, hopefully. Power rule and product rule, quotient rule, chain rule is what we've been experts at so far. Um, and we're kind of getting the idea of what a derivative is, talking about the instantaneous rate of slope, rate of change here. We should know what the verbiage tangent lines mean and stuff like that. So I think for the warm up here, these are two pretty good practice problems for you to try. So you can try number one and number two, and we'll go over those in class. All right. So let's go ahead and jump into today's stuff. All right. The title of today's lesson is higher order derivative, meaning not the first derivative, but higher than that. So like second derivative, third derivative, fourth derivative, fifth, sixth, seventh, eighth derivative. And sometimes you can take as many derivatives as you want, but we usually stop at second derivative. Like our application stops at second derivative, and you're going to see that as we move on here. It says if f is a differentiable function, then its derivative f prime is also a function, meaning it's going to be an equation, right? Like for instance, the derivative of x squared, is 2x. That is also a function. And since that's a function, then f prime has a derivative of its own. And we denote that by f double prime. It's literally just two lines. Okay? F double prime is called the second derivative. Okay, and it can also be written as this form here. Okay, so you'll see me write it that way a lot. This literally means to take derivative. We know that d over dx means take derivative of, and this just means the first derivative. Okay, so if we take the derivative with respect to x of the first derivative, then we are left with the second derivative here that I just squared. Okay, that's d2y over dx squared. That means second derivative, and we can also write it, f double prime of x or y prime, double prime. Either way is fine. Okay. Now, let's think about what the second derivative means in the context of slope. Okay. The first derivative is the slope of the tangent line. We know that. Okay, we know that it's the instantaneous rate of change at any given point x comma f of x. Now, the second derivative, all right, is the rate of change of the slope of the original curve. Wouldn't you agree? I mean, think about this. This derivative is the slope of the tangent line. All right, and that's a function of itself. Okay. Now, what do you think that the derivative of that's going to be? Well, it's going to be the instantaneous rate of change of the derivative, which just means the rate of change of the slope of the original graph. It is the rate at which the rate is changing. I think this is what the third bullet point is trying to say. In general, it is the rate of change of the rate of change. It is the rate at which my rate is changing. Now, you do, and you have seen this before, and you probably didn't realize it, but the rate at which a rate is changing is nothing more than discussing concavity. All right, concavity, concave up, concave down, being able to discuss the rate at which my slope is changing. And we'll look at a lot of graphs of that later on, and we'll look at and what that means in like the context of velocity and position and stuff like that here in a sec. So before we get into all that, let's practice actually finding the second derivative. All right? I mean, it's not hard. I mean, if you can find the first derivative, then you can find the second derivative. So, all right. Like for instance, we're given right here the function is x cosine of x. Well, let's find the second derivative. And I'm sure you already understand, if we want to find the second derivative, we must first have first derivative. Okay. All right, now, find the first derivative. Hopefully you recognize this is x times cosine of x, which is product rule. Okay. So that's the derivative of the first, which is 1, keeping the second one the same. Plus, keep the first the same, and then the derivative of cosine is negative sine. Okay. All right, that's the first derivative. Now, when asked upon the second derivative, I always recommend simplifying this down as best I can. So this is a good instance when you would simplify down the first derivative. So I mean, that's just cosine of x minus x sine of x. Just kind of write it a little bit nicer. Okay. All right. Now, the second derivative is going to be the derivative of this function here. So the second derivative is going to be the derivative of the answer I just found. Okay. So I got two quantities here. I'm going to take the derivative of cosine, which is negative sine of x, minus, and then if you notice, I'm going to take the derivative of x sine of x. Okay, so I'm going to go ahead and put that in brackets just because I know it's product rule, and I want to make sure that I know that negative distributes through to everything. So it's the derivative of the first, keep the second the same, plus keep the first the same, and then the derivative of sine is cosine of x. And if you really want to simplify that, you can, but again, if I'm asking just for the second derivative, I would leave it unsimplified. For those that do like to simplify, I think that's just going to be negative 2 sine of x minus x cosine of x. And there you go. So finding the second derivative is nothing new, like as far as math goes. Okay, it's like we can find the second derivative mathematically. It's easy. We just keep taking the derivative. But the question is what does that mean, right? What does the second derivative mean, and how do we use it? Well, the most common use, all right, the most common application for the second derivative is acceleration. Acceleration. So let's take it back a few lessons when we were discussing how velocity was the same thing as rate of change, or the slope. And we talked about how S of t is the general notation in calculus that we use for the position function. So it tells us in this particular example that the position of an object that moves in a straight line. That doesn't always have to be the case, but S of t just means where I'm at any given time, what position I'm at. After 5 minutes, I'm at 20 feet as far how far I've traveled, or something like that. Okay. But anyway, we know that the velocity of the particle, okay, v of t, is the first derivative of the position function. We've already discussed that. We know that v of t equals s prime of t, right? Which if you want to say dy over dx, you could say ds over dt. It's the same thing. Okay, so it's the slope, or the rate of change. That's what velocity is, just a rate of change. Now, what happens if I do the instantaneous rate of change of velocity with respect to time? Okay, that's the rate of change of my rate of change. All right, which another way of saying that is the acceleration of an object. So a of t is equal to the first derivative of velocity, or just the second derivative of my position function. Okay, so this right here, pretty important thing to understand, and I would really star it and really understand it and really know it. We're going to do a lot with that. Okay, and I want you to think about think about acceleration. We all know what acceleration means. Think about literally in the car accelerating. Okay, if you put your foot on the pedal, you are accelerating. What that means is when you're accelerating, you are increasing the rate of change of the rate of change. You're increasing the rate at which you are changing your rate of change. Does that make sense? So velocity is like, so velocity would be like 32 miles per hour. If you accelerate, you are increasing that rate of change. Does that make sense? So acceleration is just the rate at which your rate is changing. I know that's sound like a mouthful there, but you know what acceleration is. I mean, anybody that drives a car knows that acceleration is just the increase of your rate of change. Or if you take your foot off the pedal, you are decreasing in your acceleration. Okay, something like that. Oh my, oh my. All right. Hopefully that makes a little bit of sense. All right. Now, this is something that they love to ask questions on all the time. So let's read this closely, and we'll definitely explain it more tomorrow. But it says that the particle, okay, so we know what acceleration is, we know what velocity is. Now, this is just a definition. A particle speeds up when the velocity is positive and increasing. All right, think about that. If it's positive, all right, that means we're moving in a positive direction. And if the acceleration is positive, that means we're increasing. So we're speeding up in the same direction. So another way of saying that is V and A are both positive. Now, here's the hard part to kind of grasp. And also when the velocity is negative and decreasing. So when V and A are both negative. In other words, the particle speeds up when the velocity and acceleration have the same sign. All right. Think of everything just working together. If velocity is positive, if acceleration is positive, that means you are increasing in the positive direction. So they're working together, they're speeding up. Okay. Think about, like, if your velocity is negative, that means we're moving in the negative direction. And if our acceleration is negative, that means we're also like accelerating in the negative direction. They're working together, so we're speeding up in the opposite direction. Okay, so when the signs are the same, we're working together. All right, think of it as the particle being pushed in the same direction as it's moving. Now, if they're opposite signs, so positive versus negative, think about those like opposing forces. The object would be slowing down then. So let me write this out for you real fast. Let me make sure we're good on this. Okay, so you know, to make it clear, if V of t and A of t, okay, are either both positive or both negative. Okay, so if they have the same sign, then the particle or object, whatever we're looking at, the person, speeds up. Okay. Now, the opposite, if we have V of t and A of t, and they have opposite signs, so positive, negative, or negative, positive. Okay, so they have opposite signs. Then the particle slows down, or the person or the object, whatever we're looking at in the context of the problem, is slowing down. Now I have a visual that I can draw with this, and I kind of want to save it for live tomorrow, because we still don't have a concept of concavity yet, but I can kind of discuss that in a later slide maybe. But I can show you, and I always think of kind of a roller coaster almost with this, or like a rocket, and I can show you that later. But you'll be able to see when both the signs are positive and when both the signs are negative. You'll be able to see visually how it would be speeding up, or if it's if they're opposite signs, how that would be slowing down. To give you an example, maybe of each. And I won't do all of them real quick, but to kind of go back to the roller coaster example. And this isn't always the best example for all these things, but again, to give you an example, if you look at this, example right here. Okay. I almost don't want to do this just yet because I don't want to confuse anybody. All right, whatever. I'll do it anyway. In this particular example, okay, let's say that this is S of t. And we know that V of t and A of t are slopes and rates of change. Okay, so V of t is the rate of change of this curve right here. And we can see that the rate of change is negative, right? Can't you see that the rates of change, the slopes of the tangent lines are all negative? So V of t would be negative in this case for all those examples. Now, I kind of was hesitant about drawing this because we haven't looked at examples of A of t yet. But if you notice the acceleration here it's kind of, okay, we'll give these some values here. This is like maybe -1, and this would be actually -2 and -3, -4. Do you see how the acceleration is getting, smaller and smaller in that number? -1, -2, -3, -4. In this case, A of t would be negative. I don't want to put -1 there. Your acceleration is negative. Okay, because we're decreasing in value. All right, so hopefully you can kind of visualize that. That's what happens. The rate at which my rate is changing is negative. It is decreasing. So that makes my acceleration negative. So hopefully you can see that. Now, think about this as literally a path of a roller coaster. If a roller coaster starts at the top of my hill and it starts getting more and more steep as we're going downhill, wouldn't we be speeding up? Wouldn't we be speeding up? Do you kind of visualize how the signs are working both in the same direction, and therefore they're helping each other, and this particle is speeding up? We're going right straight down, So I try to use a roller coaster as a visual for that, and hopefully you can see that. But it does kind of help to have a better understanding of acceleration, and we'll go over that more in detail later. Okay, so for now, just kind of keep that in mind. I think it's important to star this slide, this situation right now. Okay, let's try an example. All right. It says that the position of a particle is given by the equation. So we got our S equation, which means our position function, equals t cubed minus 6t squared plus 9t. Now remember, this means position, and it tells me, where I'm located at any given time. And does it give a unit of measurement? It does not. I mean, we could be at, say, 20 feet, from our initial position. So, anywho, that's position. It wants us to find the acceleration at time t, and then it wants to know what the acceleration is after 4. Okay, it does specify 4 seconds. Okay. All right. And again, we'll, just for the sake of this problem, we'll assume that that this is in terms of feet for our position function. Okay. All right. Now, to find acceleration, we must first have our velocity function, right? We must gotta go to velocity, and that's just taking the derivative of the above function, which would be 3t squared minus 12t plus 9. Okay. I feel pretty confident in your ability to take the derivative using power rule by now. And remember, this is S prime. So S double prime, okay, S double prime of t, which is just the velocity derivative, okay, which is equal to the acceleration. Again, I want you to memorize this connection here. Is equal to the derivative of the above. So that's going to be 6t minus 12. All right. So This is the acceleration function for any given time t when given this is our position function. So if I want to know the acceleration after 4 seconds, that would be a of 4, which is 6 times 4 minus 12, or 12. Let's talk about the units of measurement here. 12, it is a rate of change. Okay, well, remember what the outputs are. The rate of change is, we'll say, feet per second, right? It's the rate at which my rate is changing. So that's the y value over the x value, or feet per second, which another way of saying that is 12 feet per second squared. And we can discuss that more in detail later as well. All right, now, to help us visualize what's going on here, it says B says use your calculator to graph the position, velocity, and acceleration functions for 0 to 5 seconds. So in your graphing calculator, graph all 3 equations that we just came up with. Or, we had an S of t, graph that, V of t, and A of t, all 3 equations, and plot them on the same graph. And we're going to make some connections here. Okay, we're going to make some connections here that helps us with part C. So I'm going to draw part B right now. And I encourage you to take time to draw a nice, clean picture of that. I'm going to do the same thing now. Okay, so pause the video, do whatever you can, take a second and draw it down. I'll give you some time, and then we'll compare pictures. So, abracadabra, alakazam, voila, there it is. So I took my time on graphing that. I tried to really make sure to graph these key aspects of it, and I hope you did too. So take a second and maybe compare your graphs here. But a couple things I want to point out here. So the green function is S of t, the red function is V of t, and the purple function is V of t. Notice how, make a connection here. Notice how, and we know what these functions are from the beginning of the problem, but notice how S of t is a cubic function. V of t is a quadratic function, and A of t is a linear function. Do you notice how it's going down in a power every single time when they're polynomials? Okay, and if you make a lot of connections here, you can compare. It's kind of interesting. Notice the maximum value and the minimum value here for the position function. Do you notice how it's the zeros of the velocity function? I wonder why that is. Because we have horizontal tangent lines here, so the derivative is going to be equal to 0. Huh? Look at this connection. Do you notice how at V of t we have a horizontal asymptote at 2? And notice how the 0 for A of t is at 2. Pretty interesting, huh? It's because, again, we have a horizontal asymptote, so obviously its derivative is going to have a value of 0. And one last little connection I'll make. Notice how to the left of 2 on V of t, it's decreasing. You see how it's decreasing here? And then notice how A of t is negative for that entire interval. It's because the slopes are negative, so A of t is going to be negative. So these are all great connections to be making at a later date. But what we're curious about now is when the particle is speeding up. Okay, this is whenever A of t and V of t have the same sign. So let's figure that out. I'll put in a little bit of chart here. V of t, I put it on a little number line, and I'll label it A of t. Okay. Now, let's just think about all the times that, for instance, like V of t is equal to 0. Okay, so V of t looks like it's, let's see, I'm listening to make sure I'm doing the same thing. It looks like that V of t only crosses 0 at, we'll call this, let's see here, and we're only looking between 0 and 5. It looks like at 0, V of t is 0, so that's good. And it looks like again at 3 were 0. Okay. And oh wait, no, I'm looking at S of t. You guys are probably thinking, what the heck is he talking about? I'm looking at S of t. I'm sorry. V of t is the red equation. All right, at 1 and at 3, there we go. So at 1 and at 3, it looks like it's positive right here. V of t has positive values right here. And between 1 and 3, V of t is negative, has negative values. So that means that in my original function, it's decreasing. And between 3 and 5, it looks like we are positive. Okay, and again, it's just negative or positive values. Now for A of t, okay, A of t, it looks like that at 2, okay, at 2, we are between 0 and 2, we're negative, and between 2 and 3, we're positive. Okay, we have positive values. So I'm just purely looking at the graph here. So when is my original function speeding up? When is it slowing down? Well, where they share the same sign is where it's speeding up. So how about between 3 and 5 and 1 and 2? It is speeding up whenever we are between 1 and 2 union 3 to 5. That's when it's both negative and both positive, where they have that in common for velocity. So if I look at my original graph, think of it again as a roller coaster maybe, between it looks like between 1 and 2 right here. Oops, I went too far. Between right here, it's speeding up. They're both negative. Think about it. We're at the top of the roller coaster and we start to go down. So we're speeding up. But then once I hit this middle point here, it starts to get concave up. Then as we shoot down to the bottom, we start to slow down because we're starting to head back up. Okay. So it's like we're slowing down. But then between 3 and 5, this is the only place where the roller coaster example doesn't make the most sense. But we're speeding up. Think of it like as a rocket, maybe shooting straight up. Okay, they're working together. So that's probably the only time the roller coaster example doesn't make sense. But again, we'll talk about how that works later on. But what I highlighted in blue here, between 1 and 2 and 3 and 5, that's when it's speeding up. Okay. Now, what I'm highlighting in black here, between 1 and 0, between 2 and 3, that's when my particle's slowing down. I guess the roller coaster example would probably help a little bit with that one. Okay. So we're slowing down between 0 and 1 and 2 to 3. Oh, and I am recognizing my time. I'm at 28 minutes. I will go over this again in more detail. I will leave you with just see how much I got left. That's okay. I will leave you with this, a summary of kind of everything we know about velocity and acceleration right now. So we've already written this stuff down. I encourage you to pause the video and write this stuff down again. But we've already discussed this piece in a previous lesson. We know what happens when V of t is 0, is greater than 0, and less than 0. So we know that it's at rest when V of t equals 0. If it's greater than 0, we're moving in the positive direction. And if it's less than 0, we're moving in the negative direction. What I want you to add to this list is what we know about acceleration now. If acceleration is 0, that means we are moving at a constant velocity. There is no rate of change of my velocity, so the velocity is constant. If A of t is greater than 0, that means we have a positive velocity. The slope of S of t is increasing. And we'll discuss that idea more later, but see if you can visualize that. And A of t less than 0 means that we have a negative velocity, meaning that the slope of my original function is decreasing. And Again, we will discuss all this in more detail later, but I'm keeping it under 30, and I got 10 seconds left. I hope you all have a great day. We will see you tomorrow. 4, 3, 2,